All right, I think I'll get started. It's a great pleasure to welcome Dan Tamayo today for our lecture TAP Dynamics Initiative Lectureship. Dan did his PhD at Cornell, starting with one of the classic problems in celestial mechanics with Cassini and Saturn. He was a postdoc at CETA in Toronto and also a Sagan Fellow at Princeton. And now he's on the faculty at Harvey Mudd, which for anyone who is not sort of from the US and doesn't know, is sort of one of the premier STEM liberal arts colleges in the country. So a really, really cool place, I think. He's an expert on planetary dynamics, chaos theory, and has recently been sort of breaking a lot of ground in astronomy using machine learning techniques. So I think he's got a lot of really cool things to tell us today. You've probably all by now received many emails both about this lecture and also about the workshop that he's offering tomorrow morning, where he's going to sort of show off some of the useful tools he's developed for celestial mechanics. So I encourage you, even if you haven't signed up, you should come. You definitely don't have to sign up in advance. Don't let that be a hindrance. And there are still a few spots in his schedule open. So if you look at any of the emails about this lecture or the workshop tomorrow, there's a link at the bottom. You can put your name on his schedule and still meet with him. So without further ado, please take it away.
Thanks. Thanks so much, Caitlin. It is wonderful to be here. I'm always blown away by just how many astro people you have, especially now that I'm at Harvey Mudd, which is this like tiny place. I was trying to think back. I think I was here 7 or 8 years ago, and I was talking about, at the time, some really exciting new discoveries of HL Tau and TRAPPIST-1, these very special planetary systems. And it was really those that got me interested in this question of dynamical stability, and that's what I want to tell you about today. And I think that's a very important problem, right? Because in our standard picture of planet formation, right, planets form out of protoplanetary disks, and there's a lot of physics going on during this stage. But after a few million years, that disk dissipates, and then you have billions of years of dynamical evolution until the gigayear ages at which we start to observe typical systems. And there's been, a lot of work over the last decade or so showing that, in particular, we think dynamical instabilities are really important in setting the final masses of planets and the orbital architectures that we see today. Right, so the question that fascinates me is like whether we can predict what types of orbital configurations will eventually go unstable, and what the mechanisms are for driving those instabilities and driving that chaos. Because if you think about it, it's kind of a surprising phenomenon, right? Like, it's not like we're doing fluid mechanics or solving some partial differential equations. We have no magnetic fields. You couldn't ask for a simpler force law than GMM over R squared. And the forces are tiny, right? Like if you're a planet in a system of super Earths, the gravitational forces that you feel from other planets are something like 10 to the minus 4 of what you feel from the central star. Okay, and what's more, because all the planets are going around at their own speeds, sometimes you're getting pulled forward, sometimes you're getting pulled backwards. So you would think that all these things should just like average out. So why is it the planetary systems, planets don't just orbit indefinitely in their ellipses, and then the orbital elements just sort of oscillate? I think that's actually a really interesting question. It's a beautiful question. It's actually a really thorny one that we've been wrestling with like for over 300 years. Okay, so as maybe a historical perspective, right? Like around 1700, Newton started worrying about this for the solar system. That like, well, if you let the solar system go, then maybe things start to go a little haywire, and he concluded that maybe God periodically has to intervene to put things back into order. About a century later, Laplace and Lagrange, basically thought that they proved the stability of the solar system because they found an approximate solution for the dynamics in terms of normal modes, where you could just write down what each of the planet's orbits would do as a sum of these Laplace-Lagrange eigenmodes. So the fact that you could write it down for all time precludes the possibility that things could change and things could go haywire. Right? Another century later, then Poincaré comes along and says, forget about even trying to understand the entire solar system. If you take Newton's solution to the two-body problem and you just add in one more planet, right, like three-body problem, then you open up Pandora's box and the possibility of aperiodic and chaotic motion. Okay, so here we are another century after that, and we still haven't figured it out. So, what do we know big picture, like theoretically, before we even start thinking about this problem? Decades of nonlinear dynamics tell us that in systems like this one, where you're subject to a periodic conservative potential like gravity. Okay, so periodic in the sense that you have all these planets going around, you have these orbits, all those angles. If you cycle one of them by 2 pi, then you have the same potential back. Conservative in the sense that gravity conserves energy. In that sort of situation, chaos is generically driven by the existence of integer ratios between different frequencies in the system. Okay, so we know it has to be resonances. It's not obvious which resonances. Okay, so we have the rates at which planets go around the star. So resonances between two planets' orbital periods, those are mean motion resonances, or MMRs. Those happen quickly. There's also the much slower rate at which the orbits themselves precess, right? So if you have two orbits and their precession rates match up in an integer ratio, then that would be a secular resonance, and that happens much slower, right? So the fact that planets are going around much faster than the orbits are precessing means that MMRs can drive chaos much faster than secular resonances. Okay, there's also other types of more exotic types of resonances, but those are the two main ones that matter for what I want to talk about today. Okay, so the two key properties of MMRs that we need to understand in order to make progress on this question are, first, that MMRs have finite widths. Okay, so that maybe gets at a question that I had early on at least, and that is, say I have a MMR like the 3:2. So does that mean that my two planets have to have a period ratio of exactly 1.5? Okay, the answer is no, is that MMRs have finite widths or extents, so that if, for example, I started with a period ratio of like 1.503, then what will happen is my period ratio will oscillate around an equilibrium period ratio of 1.5. Okay, so why is that? That's the first one. The second one is that the strongest MMRs are of the form n to n minus 1, so like 2 to 1, 3 to 2, 4 to 3. Okay. That should be really unsatisfying, at least it was to me. And I think we've come up with a simple explanation for why that is, that I'm really excited about. But let's first start by trying to understand why MMRs would have finite widths, just like taking this as a given, because it will help us. Okay, so if you think about the problem generally, it can be complicated, but one approximation that helps a lot is that all these strong first order MMRs, where there's a 1 difference between those two numbers, those all lie at close separations. Okay, so if I have a star and I put a planet on a 1-year period, then the locations in which I would have to put a second planet, and they would be in this 2 to 1, 3 to 2, etc., those all lie quite close. Okay, the furthest one, the 2 to 1, lies at a fractional separation, delta A over A, of only like 0.37. Okay, so making the approximation that delta A over A is much less than 1 actually helps a lot. Okay, so why does that help? Well, if you have 2 orbits and they're really close to each other, then you don't really have to worry about all the details of how these planets are interacting as they go around their orbits and integrate up all their effects. Your dynamics is going to be completely dominated by the close encounters that planets have each time that the inner planet overtakes the slower outer planet at conjunction, right? Because their GMM over R squared is way, way bigger than at any other time, right? Okay, so for simplicity, let's make this a star. Let's make this a massive planet on a circular orbit. And then this is going to be a test particle with no mass on an eccentric orbit. Okay, so as a result, this planet has a 2-body problem. It doesn't see this planet. So it's always going to stay on a circular orbit. And then we can just focus on what the test particle will do. Okay, and I've aligned the orbit so that because of the eccentricity, the orbits are closest together here, and they're furthest apart over here. Okay, well, if we'd like to understand why the period ratio would oscillate around some equilibrium value, we need to think about energy, right? Because the Kepler problem has this funny property that it only depends on the 7 major axis. And, the 7 major axis and the period are related by Kepler's 3rd law. So you can always go back and forth. Okay, so if we think about how the energy is changing across one of these conjunctions, okay, E dot, the work that you do is just the force applied dotted with the velocity. Okay, so if we think about this test particle, as the inner planet is approaching conjunction, okay, the test particle is moving to the right and it's being pulled backwards in its orbit, right? The planet is extracting orbital energy from the test particle's orbit. So E dot is negative as the planets are approaching. But then as the inner planet overtakes, now the inner planet is ahead. So as the test particle is being pulled forwards in its orbit, and it feels a positive E dot. Yeah. Okay, so the total change in energy for our test particle is then just going to be the integral under this curve. Okay, and if both of these orbits were circular, these 2 peaks would be symmetric. Nothing would be different before and after. But you can see that this peak before conjunction is actually deeper at like minus 350 in whatever units these are. And here it only reaches 200. Okay, and the reason for that is the fact that here the orbits are closer together and here they're farther apart. Okay, so as we're approaching conjunction, if conjunction happens over here, then before conjunction, the orbits are closer together. So they're interacting more strongly. After conjunction, the orbits are farther apart and they interact less strongly. That gives you this asymmetry, right? So we'd expect the effects of these conjunctions to be, maybe some complicated function of the eccentricity and the azimuthal angle where this happens. But if you Taylor expand that for small eccentricities, you'd expect it to be linear in the eccentricities. Okay, so the key thing, right? Like if you zoned out on that explanation, like the key concept that we need in order to understand this in a broad picture is that if the conjunction happens anywhere to the left of this line, where you're going from closer together to further apart, then this part, the test particle is going to lose orbital energy. Okay. If you lose orbital energy, you're going deeper in the potential well, which means that your orbit speeds up, right? Like Mercury orbits faster than the Earth. It's like Kepler orbits have this funny property that when you lose energy, you gain angular rate. Okay, so here our test particle speeds up, but if the conjunction happens over here, you have the opposite case and you slow down. Okay, so that's all we need to understand these first order MMRs. Okay, so I've initialized these two orbits with a ratio of their mean motions, the angular rates at which they go around. They're in a 10:9 ratio. Okay, now if these planets didn't interact at all, then after 10 orbits of the inner planet, the outer orbit would do 9 orbits and they would meet here again. So the conjunctions would just keep happening here, right? But because they meet here and this planet does have mass, our test particle is actually going to speed up. Okay, so at conjunction, the test particle speeds up and it now moves a little bit faster than it did before. Okay, and as a result, now after 10 orbits of the inner planet, the outer planet is going to do 9 orbits and a little bit more. So that means that the next conjunction needs to happen further along. It's going to happen over here. And again, it's happening to the left, so it speeds up. And then it moves further along. It moves further along. But once you cross this line, now successive conjunctions slow down our test particle. So this period ratio or mean motion ratio is going to start now decreasing, right? We're still moving too fast for the resonance, so we're still sweeping to the right, but we're slowing down. And once we reach the resonant value again, now we're going to start falling backwards. Okay, so if you let this go, instead of looking at individual conjunctions, is these individual exchanges of orbital energy at conjunction that are giving rise to these periodic oscillations around the equilibrium value of the period ratio. Okay, so that's all that we need in order to try to understand what is setting stability in these compact multi-planet systems. Okay, so it turns out that there's a qualitative difference between systems that have 2 planets and systems that have 3 or more that are actually really interesting to think about. Okay, the 2-planet case is effectively solved, and it will help us to understand how things work in this simpler problem before we try to tackle this one. Okay, so again, let's take a star and 1 massive planet. Now we're going to make it the outer planet with an orbital period of 1 year. And now we're going to put in a test particle somewhere in here, and we're going to vary where we put it. Okay, so as we change the orbital period of this inner planet, we're going to find locations where the orbital period has an integer ratio with this outer one. Okay, so the name of the game is to take each of these MMRs and map out the resonant regions corresponding to each one. Okay, so take the 7 to 5 at a period ratio of 1.4. Okay, so if you're like not exactly at 1.4, but you're a little to the right or to the left, as long as you're in this gray region, you're going to oscillate around 1.4. If you're in the white region, then you'll just stay here. You don't oscillate. You're not in the resonance. Okay. So the idea is that if you have the ability to map out resonances in this way, then in regions where the various resonances are well separated from each other, you will have perfectly regular, non-chaotic motion. Whereas in regions where adjacent resonances start overlapping one another, that's sort of the criterion for where you'd expect to see chaos.
Yes. Could you explain in more detail what the y-axis is?
Yes, right. So on the y-axis, okay, so on the x-axis, we're just varying the period where we put this planet. On the y-axis, we're making this orbit more and more eccentric. Okay, so this is a circular orbit, and we have normalized this y-axis so that the top corresponds to orbit crossing. Okay, so we'd expect that when orbit starts to cross, things are going to go very badly. And here things are circular. And like we talked about, right, like what's causing this oscillation is the asymmetry before and after conjunction. So the more eccentric you are, the bigger that effect is. Okay, so it makes sense that the widths, the size of the resonant region grows as we make our test particle more and more eccentric. And it's that property that essentially guarantees that as you scan upwards in eccentricity, eventually you're going to find a location where these resonances start crossing one another. This is actually a beautiful paper by Sam Haddon and Yoram Lithwick that came out in 2018 that generalizes sort of a classic result from 1980 from Jack Wisdom that corresponded to 0 eccentricities. Okay, but Sam and Yoram generalize it to sort of the full coplanar case, so that you can map out as a function of all the possible orbital periods and eccentricities where you'd expect things to be chaotic, where you'd expect them to be regular. Okay, so the colors here are actually the result of numerical integrations. Okay, and what they're doing is they're like running n-body, and they are measuring the chaotic time scale in the system, the Lyapunov time scale. Okay, so as you go from red to orange to yellow, that chaotic time scale is getting shorter and shorter, as you would expect, as things are getting closer and closer to orbital or orbit crossing. Okay, so that sort of big picture says that as long as we have some way of mapping out the extents of all these resonances, then we have a theoretical framework in which to figure out where things should be chaotic and where they shouldn't. Okay, the tricky part is figuring out the widths of these resonant regions. Okay, and if you go to papers in the literature of celestial mechanics, it can get quite complicated. So this is a paper by Kat Deck and collaborators for first order mean motion resonances, the strong ones we were talking about, like 3 to 2, 4 to 3. And if you go into that paper, you can find that like the resonance width is just this 4 over root x3. And you would ask, well, okay, so what is x? And x is this thing. And then yes, what is phi prime? And it is this thing. And then q is this thing. And then you ask, what is psi? It is this thing. And all of these depend on numerical coefficients that then have to be tabulated. So if you have the 2 to 1, then you need to use this number and this number. If you have a 3 to 2, you need to use this number and this number. And these are the numbers that you find in the appendix of like Murray and Dermott solar system dynamics. Okay, so, we've developed this mathematical machinery used here, which is Hamiltonian perturbation theory. Yes?
Is that just some linear stability analysis or kind of?
No.
Okay.
So this is like starting from the general Hamiltonian for this 3-body problem, star and 2 planets, and then doing a whole sequence of canonical transformations, expanding around the resonance, and making lots and lots of changes to variable that pop out all these conserved quantities and let you reduce things to a 1 degree of freedom system. Okay, it's a really powerful technique because it gives you conserved quantities. It gives you a really detailed look at what's going to happen, like for your particular planetary system close to one of these resonances. But it's not super helpful in this sort of situation where you want to look at like a whole network of resonances, right? Here are the first order ones for which those equations would apply, but you have a whole other set of equations for the second order resonances where there's a difference of 2 here, and a whole other set for 3 third order resonances, and you want to put them all together, and it's just like hopeless. Okay, so the beauty of this paper in 2018 by Sam Haddon is that he realized that there's ways of simplifying this if you make that closely spaced approximation. And he showed that in the language of Hamiltonian perturbation theory. Okay, but in this paper that was just accepted in AppJ that's on the archive now, we tried to sort of translate that into simpler physical arguments. Okay, so like all of this mess, it turns out that you can write the same widths, like how wide the resonance will be. All you need to know is you need to know the order of the resonance, right? The difference between these two numbers. Okay. It's obviously going to depend on how massive the planets are. So this is the dimensionless ratio. How massive are the planets relative to the star? If you make them twice as massive, then the resonances, right, like the strength of the resonance will be twice as big. And you know, the key insight that Sam had was thinking about these eccentricities in this way, like not what is the absolute eccentricity, but what is the eccentricity as a fraction of the orbit crossing value. Okay, the reason is, like, you know, an eccentricity of 0.01 might be pretty small if you're talking about like the 3 to 2 resonance where the planets are well separated. But if you're talking about like the 31 to 30, and you can find resonances like that in Saturn's rings, okay, then an eccentricity of 0.01 could be like right up against orbit crossing, or it could be orbit crossing. So thinking about your eccentricity as a fraction of crossing lets you think about different resonances on the same level. Yeah. Okay, so with just these numbers, what we show in this paper is that you can show that the width of the resonance, instead of this, just looks like this. Okay, you have one numerical coefficient that is of order unity. So for first order resonances, this is 0.85. Okay, as opposed to the whole table for all the first order resonances that each had different numbers. Okay, and the scaling is very simple. It goes as the square root of this mass factor, and it goes as the square root of this eccentricity, normalized eccentricity to the qth power. Okay, and that works for resonances of any order, whatever n and n minus and q are in this thing here. Okay. This will fail at the smallest eccentricities, and Reinu will tell you that it will fail at the highest eccentricities, but it actually works quite well over a broad region in between. Okay, so this is from the paper showing you, like, for a first order, a second order, and a third order mean motion resonance. These are numerical integrations where the color is telling you the time average value of this period ratio, where we've just like shifted things so that the resonance is always at 0. Okay, but this is period ratio. Okay, so if you're in the white region, that means that your period ratio averages to the resonant value. So you're oscillating around the resonance, but it averages out to 0. But if you're blue or you're red, then you're then outside the resonance. Okay, and these dashed curves are just the predictions from that single equation for all 3 of these resonances in that way. Okay, and that's a huge simplification that allows you to look at like networks of resonances and look at where these different resonances might start to overlap. Yeah.
Is the structure in the white region, it looks like somebody like rubbed an eraser on some red fuzz.
Yeah.
Is that, I mean, there's like little white lines. Is that from the numerical integrations, or is there actual structure in that oscillation?
Yeah, no, so there definitely is structure in this oscillation. And the issue is that you're not exactly symmetrically oscillating above and below the resonant value. Like you can be offset, the mean value can be slightly offset depending on like how deep you are in the resonance. And that's the issue, like those things become a big deal at low eccentricity. So you can see that there's a big discrepancy down over here. Okay, and to do that, you need a more complicated model for resonance, like a second fundamental model of resonance. And we're actually like working on a paper that does that. You can still do all the same things and use this simpler language, but it's just that that model is a little bit more complicated. It has one extra parameter compared to this pendulum approximation, which is what we're doing here. Okay, so that's why MMRs have finite widths. We now have an equation that is simple for estimating how big those different resonant regions are. I also wanted to talk about, you know, this question of why the strongest MMRs are of this form of n to n minus 1, because this is something that always bothered me. And I want to like state it in a different way that I think raises the stakes, right? So one question that you could ask here is we put the first order resonances. Here's a second order resonance. We put third order, fourth order, fifth order, okay? But at what point do you stop? Right, like the real number line is densely covered by the rationals. There are resonances everywhere along this line, right? So why isn't it that everything is chaotic, right? There's resonances everywhere. Why aren't they overlapped everywhere? That's a really fundamental question. Yeah. And, you know, a dynamicist would tell you, well, you know, they wouldn't write it like this, but they would be able to tell you that the width of a resonance scales as e to the order of the resonance with a square root. What that means is that at least as long as you're at low eccentricities and this e tilde is small, then you know, there might be a resonance here that is like 373 to 212, but then you have some enormous power of the eccentricity so that the width is like completely suppressed. Okay, so it's this exponential dependence of the resonance width with the eccentricity that makes it possible to ignore the whole forest of higher order resonances. Okay, but that's not like satisfying, right? Like the question is why? Why do these widths scale with the eccentricities in this way? And you know, going through this exercise of trying to understand resonance widths in this simple way actually helped us understand this in a new way that I've never seen before in the literature, and I'm actually really excited about. Okay, so we've been thinking about first order resonances, but imagine a second order resonance, like maybe this is 13 to 11 or something, right? Well, in terms of everything that I've said to you, like these planets are still going to orbit and they're still going to have all their conjunctions, right? So like the question is, what is different about this picture compared to everything that I showed you before? Okay, well, the difference is, say I take the 7 to 5. Okay, so if the inner orbit does 7 orbits for every 5 of the outer one, it means the inner planet has to overtake twice, right? So it means you have to have 2 conjunctions per resonance cycle. Okay, so imagine that your first conjunction happens here like it was happening before. Okay, well, everything is orbiting at nearly Keplerian rates. So if you wait 1 full resonance cycle, you expect this to repeat. You should be back here after 1 full resonance cycle. But in 1 resonance cycle, you have 1 extra conjunction. And because everything is moving at approximately constant rates, it must mean that then the second conjunction happens here. So that means that you are having 1 conjunction where your orbits are getting farther apart and you speed up. But then your other conjunction, like by construction, needs to be at a location where your orbits are coming close together and you slow down. Okay, so the idea is that the reason why higher order resonances are weak is because you have multiple conjunctions per cycle and they all cancel out with each other. Okay, so here's a numerical demonstration. Okay, I'm labeling this conjunction in red, this conjunction in blue. Okay, and here I'm just running a numerical experiment where on the x-axis I'm varying how eccentric I make the outer orbit. Okay, so as I do that, my conjunction should get stronger as I increase that asymmetry. And then I'm just using rebound to measure how much my mean motion changes. Okay, so when I look at the magnitudes of the individual conjunctions in red and in blue, I find that the magnitude of the kicks scales linearly in eccentricity as I would expect, like from everything that we talked about before for first order mean motion resonances, right? Like think of some complicated function of the eccentricity. At low eccentricities, you can Taylor expand and it should be linear in the eccentricity. Okay, but then if you take into account the sign and you add up these two conjunctions, you get the green curve. And you can see that for the second order resonance, the size of the kick to the mean motion scales as eccentricity squared. Right, so it's the fact that these two conjunctions have canceled to leading order that gives you the higher order scaling in eccentricity. And that, I think, is a really like nice physical picture for why higher order resonances are weak, and we only have to think about the low order resonances in planetary systems. Yes.
This works because at very low eccentricity, the linear terms are the same absolute size. Is there an intuitive understanding for why this is the case?
Could you say that?
So in your Taylor expansion, you have the same coefficient for the linear term for the two resonances. Otherwise, they wouldn't cancel in. Is this intuitively clear why that is?
Okay, so one thing that you might worry about, I'm not sure that's what you're worrying about, is that like when I have this conjunction, things are going to change slightly so that things aren't exactly the same as they are over here. So they shouldn't exactly cancel.
Yeah.
Is that right?
Yeah.
Yeah. So the key, I don't know if I can go back enough, is that if you look at the full oscillation and period ratio, right, is that sinusoid that is the resonant dynamics. But that resonant dynamics was built up of lots and lots of individual conjunctions. So the approximation is that while it is true that there's a very slight difference before and after conjunction here, like they're almost the same.
Yeah.
So it's the fact that you have many conjunctions per oscillation that allows this argument to work.
Okay, thanks.
Yeah. Yes.
Is there any influence here from just the time scale of a much bigger number of resonance? Is the repeat time taking much longer for the resonance to do anything?
I'm not sure. I mean, one thing that is tricky here is, right, I can show you this for a second order resonance. Like, you know, we can understand that the leading order scaling should be linear and that should cancel out to leading order, which would give you E squared. Okay, but if you take a third order resonance, what you would have to say is that things don't just cancel to leading order, but that things also cancel at second order, leaving you third order leading scaling. And it gets worse and worse as you go to higher and higher order. Okay, so, you know, the simple paper that we tried to write was not the right paper in which to explore that. But I am looking at this with a student at Harvey Mudd doing her senior thesis with me, Lizzie Jones, who's actually done a really amazing job. Okay, so if you want to do this, right, so this is a fifth order MMR, so you have 5 conjunctions per cycle. So if you want to do this, you really need to know, like, not just what is the leading order effect of conjunction, but what are all the higher order terms. Okay, so you have to Fourier expand this complicated interaction to get all those various different terms. Okay, and what you find is, right, like this is showing you E1 terms for this fifth order MMRs. We could do the same thing with the E squared terms, E cubed terms. These are all terms in this like Fourier expansion. Okay, and she came up with this way of thinking about all these kicks as vectors in this abstract space, where the goal to calculate the total size of the kick involves adding up these vectors, right, like head to tail. Okay, and the fact that you have 5 conjunctions per cycle, and they have to be, because things are moving at nearly Keplerian rates, they have to be equally separated over 360 degrees, means that if you add these head to tail, they actually come right back to the origin and cancel back to 0. This is actually exactly what comes up when we look in electricity and magnetism at descriptions of diffraction through multiple slits. You build up these phasors and you come up with this geometric picture where this like destructive interference give you things like this. And it was really cool that she used the same thing for understanding how these different kicks add up. Right, but this is, we're working on this now, but like this is the sort of rigorous work that you have to do to show that like the simple picture that I'm explaining in words actually works in detail when you go to higher order and do this carefully. I don't think that at all answered your question.
That's okay.
But we are going to talk about some longer time scale things. Yeah. Okay, so that's the picture for 2 planet systems. Okay. Unfortunately, most planetary systems have more than 2 planets. Okay, and people have for the last 3 decades been just running n-body integrations of 3+ planet systems and just measuring how long these different configurations take to go unstable and trying to like find patterns and fit different curves to that behavior. I've been guilty of this, but like we've had no other way of trying to get at like how long things take to go unstable in these different systems. Let's see. So like one thing that those numerical experiments have shown very, very clearly is that when you go from 2 planets to 3 planets, things go unstable and become chaotic over a much wider range of interplanetary separations. And what's more interesting is like, well, when you go from 2 to 3, there's this big difference, but it's not like then when you go to 4, there's another big difference. The differences get smaller, and going from 4 to 5, they get even smaller, and eventually you saturate, and adding more planets doesn't make a big difference in these compact configurations. Okay, so that's good, because otherwise we'd have to like do the 2 and then the 3 and then the 4. And I think that, after working on this for a while, and other people have worked on this for a while, I think there's a simple explanation for why that is. The sort of going like 3 planet systems are maybe like the elemental building block for understanding stability in more complicated systems. And that is the following, right? So imagine that you care about this planet here in red, and we just have the 2 planet system that we were looking at before. Well, we know how to analyze that. Like we know how to look at the resonances and see where they are and where the boundary is. Okay. But when you go to a 3 planet system, now you're adding another close neighbor on the other side, right? So like this neighbor is affecting this one just as much as that one. But then when you keep adding more and more planets, right? Like maybe this one and this one sort of matter for this one, but the further you put these planets, the less they're gravitationally interacting with the red one. Okay, so maybe we can try to understand 3 planet systems and use that to understand the dynamics of higher multiplicity systems, at least in cases where they're compact. Okay, so the problem is that introduces a lot of new complications that didn't exist in the 2 planet problem. Okay, so I'm just gonna outline what those are. The first I've labeled 0 because this is pretty straightforward. Now you have 2 sets of MMRs to deal with. Okay, so when we had 2 planets, we could make this plot. Okay, and notice that the boundary for chaos is sloping down this way, right? So, right, remember that the planet was out here. So as we move our test particle closer and closer to the planet, we can see that the boundary shifts towards lower eccentricities, like we'd expect. Yeah. Now, when we add the second planet, you sort of get squeezed from both sides. I didn't want to make a new plot, so I just flipped it. Right? But now things are getting worse as you move towards this planet that is here to the left. Okay? So, you know, it's pretty straightforward to put these 2 things together, and we looked at that in this paper in 2021, and you know, you can see that sort of qualitative feature where things like that boundary towards chaos is sloping down as you go this way, and it's also sloping down as you go the other way. Okay, so that's not a big deal. A qualitatively new phenomenon that arises, though, is the possibility of 3-body mean motion resonances that have been discussed in a series of really amazing papers. And the idea there is, right, imagine that you have an inner neighbor, an outer neighbor, and your test particles, say. And here is a resonance with the inner planet at 7 to 5, and here's another resonance with the outer planet at 9 to 11. Okay. Now, everything that I've talked to you about works in terms of like calculating the widths of this region and the widths of this region. Those all come from a model in which you just consider the existence of a single resonance and nothing else in the universe. If you make a dynamical model for a system that has 2 resonances in it, you will get the same thing, but in addition to that, you will get a whole forest of 3-body MMRs in between, right? These are secondary resonances that come from the interaction of these 2 resonances, right? These resonances introduce new frequencies into the system. So integer ratios between this frequency and this frequency gives you a whole other set of 3-body MMRs. And this is what like generically gives chaos in these conservative systems, this like beautiful fractal structure that you can have resonant islands, but each of those resonant islands gives rise to a whole second set of secondary islands. And then each of these secondary islands will give a set to tertiary islands all the way down, right? It's turtles all the way down. Okay, so the empirical puzzle that this was trying to address is that, you know, in the 2-planet case, when you looked at low eccentricities, you would find that like these regions are all regular, they're not chaotic. When you go to 3-planet systems, you can find chaos even at low eccentricities. And that is really hard to explain, right? Right, because at low eccentricities, this resonance and this resonance don't overlap at all. But the fact that these resonances now give rise to this network of 3-body resonances, each of which that will have their own widths, now makes it possible for 3-body resonances to overlap and drive chaos. Right, so these papers actually did a really amazing analysis of, you know, identifying the network of the most important 3-body resonances, calculating their widths, and seeing where they would overlap. Yes?
The argument that you used for explaining why the higher orders get suppressed for 2-body MMRs, can the same argument be used for 3-body MMRs, or are the higher orders actually important?
I don't know how happy that question makes me. You know, so I showed you like that paper for 1st order 2-body MMRs that was really complicated. Okay. Antoine Petit, right, that was for 1st order 2-body MMRs. Antoine Petit wrote another paper calculating the widths for 1st order 3-body MMRs. And I'm not even joking, like the expression for the width spans 4 appendices of special functions for one of them. Yeah, and then you need to like take one of them and do the next one and the next one, and then figure out where they all overlap. It is an absolute nightmare, right? Like it shows the power of this Hamiltonian perturbation theory to just crank out results, but like to me that's sort of like a dead end. But exactly, right? Like if we can understand what is going on at each of these conjunctions, these 3-body resonances become really easy to understand, right? You have one kick from your outer neighbor, and then you get another kick from your inner neighbor. And by adding up these kicks, you should be able to get much simpler expressions for the widths of these resonances and how they scale with the masses and how much mass you put here, how much mass you put there. So that's exactly what we're working on right now.
I'm just flagging that we have a couple minutes left, but
Yeah.
given that there have been questions along the way, then I think it's okay to expand a little bit.
Okay, I'm close to done. Yeah, thanks. Okay. The other new effect that comes in is all to do with secular dynamics, which is what I brought up at the beginning, right? So you have these interactions that happen at conjunction that give rise to this resonant behavior. But, you know, the other thing that you can do is you can play the movie in fast forward, where you don't even see where the planets are along their orbits, and they just become like rings of mass. And you can calculate the interaction between rings of mass. Right? That's what Laplace and Lagrange did. And what you find when you do that, right, like in these simple models, we were approximating the eccentricities as staying constant, which is actually a pretty good approximation at like middling eccentricities. And that's what allowed us at like one value of the eccentricity to calculate what the width is. Okay, but now we're saying that on this longer time scale where the secular dynamics operate, and maybe that's like related to the question that was asked earlier about longer time scales, the secular dynamics say that these eccentricities should undergo long-term oscillations, right? This is what causes ice ages on Earth, okay? So that introduces a complication, because if your eccentricities are slowly changing and the widths of these resonances depend on the eccentricity, it means that your resonances are slowly getting wider and they're slowly getting narrower. Okay, so this is taking this plot and just turning it sideways. Okay, so this is a 2-planet system where here is showing you the resonances. We would say that here is where they start to overlap. So here we'd expect it to be chaotic right on the right. Here it should be regular. Except now we're going to add a third Jupiter sort of far away. Okay, far enough away that the resonances with the Jupiter don't change this picture, but they do induce secular dynamics that cause the eccentricities to change. And when you do that, and you run the numerical experiments, you don't see the boundary happening here. It happens way to the left, right? Here are the regular regions, and yellow are the chaotic ones, okay? But if the picture is that the secular dynamics is changing what your eccentricity is doing on long time scales, 10,000, 20,000, 30,000 years, then we can take how much the eccentricity changes by and just update what the widths of our resonances look like. Okay, so this is the picture at time 0, but what we're saying is that this should be a movie, right? As the eccentricities go up, they all get wider. As the eccentricity goes down, they all get narrower, right? So the resonances breathe in and they breathe out on this longer time scale. Okay, so the idea is we shouldn't be calculating where do the resonances overlap initially. We should calculate where do they overlap at the maximum in the eccentricity cycle. If you do that, that's like down here where they start overlapping. And that's what matches the numerical results down over here. Okay, so we had to calculate all the secular dynamics numerically. That's like, you know, Laplace Lagrange figured it out. It requires a matrix inversion that you usually do numerically. Eritis Yang is an incredible student at Harvey Mudd who looked at this problem. She's now a grad student at Princeton, and she made that closely packed approximation again and took a 3-planet system and like tried to use that approximation to invert that matrix analytically. And that was a really complicated problem. Like it's it's super technical, and she had to figure out what are the right approximations to make things like, how should you parameterize things to make things simple to understand. She wrote this paper in like 6 months, like knowing nothing beforehand, which I'm pretty sure is faster than I would have been able to write the paper, like working on it full time. Like she is absolutely out of this world. The AAS doesn't have a prize for undergrad research, but the American Physical Society does. And she won that last year as the APGAR Award. And she's actually giving her prize talk now in LA. And I couldn't go to her talk because I'm here, but I got to see her over the weekend. So she came up with analytic expressions for how much, this boundary should get pushed down by the secular dynamics. It's a really amazing paper. Okay, so those are the 3 new effects. The other one that I didn't talk about is the possibility of resonances between these secular frequencies. Renu and others have worked on that. But I should finish. Okay, so the summary is we understand how to map out chaos in 2-planet systems. It helps to be able to write down simple expressions for these resonance widths that has applications not just for chaos and stability, but for all sorts of things in exoplanets. And I also gave you this argument that high order resonances are weak and narrow because of these canceling effects of multiple conjunctions. The frontier is trying to understand 3+ planet systems. We're still working on this, but at least we have a picture of what the qualitative effects are. Right? So we have different sets of MMRs. We have these 3-body MMRs that I'm excited to actually work on more. And we figured out that there's this longer dynamical timescale in the problem that can, make this also time dependent. So I'll stop there. Thank you.
I'm your new moderator. Thank you. That was fantastic. Thank you. Are there any questions?
So, not sure how applicable this question would be, but in general, if you have planets that are far away, possibly you could use like linear perturbation theory arguments on a circular orbit or like an orbit of a fixed eccentricity to see how it would evolve. And
Can you say the first part again? If you had a system with what?
If the planets are far away, then the perturbations of one planet on the other are possibly weak enough that just in linear theory, it might be tractable to deal with it. And if the planets are close enough, then perhaps you can expand around the resonances. I'm curious how tractable or how important are the intermediate cases?
I mean, at some level, everything that we're doing here in terms of taking one resonance and calculating this width, that is expanding in a really local region around this location and doing the kind of thing that you're talking about. The tricky thing comes in like how, you can do that when you just take into account one resonance at a time. The tricky thing comes into play when you have more than one resonance that's important. And, the fact that the simple criterion is to say, well, if those overlap, then things are going to be chaotic. And if not, no. In reality, things are more complicated. And if you want to go into it in detail, then you have to model these secondary resonances and look at the overlap of those. And it becomes very complicated very quickly. So we've been trying to sort of go the other way and simplify things as much as possible. Any more questions? No, go ahead.
In the regions of chaos, does it always like result in some catastrophic event, or could they just go around in that chaotic place for a long time?
Yeah, so that's a great question that I've completely skipped over in this talk. Right, so for sure, if things are regular, then, whoops, I don't know what if things are regular, then the oscillations are gonna be quasi-periodic. They'll just sort of basically repeat. Okay? So if you want to have instabilities, you need chaos, like it's a prerequisite. Okay? But it's a separate calculation, right? So I've been telling you, like, when should you expect things to be chaotic? But then once things are chaotic, it's a separate question of like, how do things move through those like chaotic regions in phase space, and how long do they take to find the point where the orbits cross and blow up? I think, well, I don't know. Everything is hard, but at least doing them one at a time is helpful. My feeling is that, like, if you find regions that are chaotic, the lifetimes of planetary systems are so long that in general, like in the chaotic regions, they'll eventually find their way out, and that it doesn't really matter. But it is an interesting theoretical question to model that transport through phase space. Yes.
Do you think you could make the slide deck available to the mailing list?
Sure. Yeah, no problem.
Thank you.
And this is being recorded as well. Do you have a question?
Oh, no.
Yeah. Yeah. So at some point, can we change the third body by a belt, even when could be roughly axisymmetric, could have some impact on the two-body system? Like, I don't know. I'm thinking or cloud or.
Yeah, I mean, or for like this experiment that I showed you, it would be totally fine to replace the Jupiter with a circular Jupiter with all the mass spread out in its orbit, because, like, you know, we were just relying on it to give us the secular dynamics, which, you know, that's the approximation that we're making. But, you know, everything about the mean motion resonances really does rely on having like the mass in one place and the things going around and having resonance between the rates at which they go around. Yeah. Yes.
In all these numerical experiments that you've done, are all the particles coplanar or initially coplanar?
Yeah, wonderful question. So yeah, I think for these, they are coplanar, but that's something that we've looked at, right? Like, you might wonder, like, what if things are not coplanar? And what we found by just running things numerically and making these like maps of chaos is we find that for small inclinations, which might be typical of transiting systems, the maps look exactly the same, like within like 5 degrees of coplanarity. For sure, if you go to like 40 degrees, then you're going to have things like Kozai oscillations, and it's going to be a mess. But, you know, at least for systems, say like with inclinations like in the solar system or like in transiting planets, modeling it as coplanar is good enough, and it's actually a big simplification to reduce those degrees of freedom. Yeah. Yes.
There's a question on Zoom.
Oh my gosh, you're right.
That's so considerate.
Now I have to figure out how to. Yuchia? Can you hear
Hello.
me to ask your question? Do I need to unmute you somehow?
Could you hear me?
They are
Could you hear me?
speaking, but I can't hear them. Is there, do you remember when they set you up?
I'm
If
not
they
sure.
muted anything? Are you
Would you
muted
be
over
able-
here?
Would you be able to
Yeah,
type in
can
the
you hear me?
that might take less time than it would take for us to figure out
How about this one? I can type it.
with technology.
Can you hear me? No.
No.
Yes. I'm assuming that they're typing.
Oh, boy.
Meantime, is there anybody else in the audience who has a question? Yeah, go ahead
Yeah.
while your Chia types.
So thanks a lot for the great talk. This is a beautiful framework for understanding stability of mature systems. So if I want to understand architectures of resonance systems, I'm also interested in the question, how did they get into the resonances? And then probably dissipation plays a big role, either dissipation in a disk or some other mechanism. So is there a way to integrate that into this framework, or do I have to start with something completely different to take into account dissipation?
I think that is more complicated. Okay, so part of simplifying this in order to understand things is it's just isolating interactions between pairs of planets to take individual resonances and build up all the resonances and see where they overlap, etc. But if you have like TRAPPIST-1, where you have a chain of resonances, then you can't just look at it as like pairs of planets, and you have to do something more complicated. So Jean-Baptiste Delisle has a really nice paper on chains of resonances like TRAPPIST-1. And that's in like the Hamiltonian perturbation theory picture. There's no simple answers there. But yeah, I think resonant chains are intrinsically more complicated to analyze. So it's good we don't have many of them today.
I'm noticing the time, so I want to make sure that Yuchia is able to ask a question, but maybe we should take it offline. And let's thank Dan one more time for this really